air outlet selection. The design and selection of air distribution equipment in today's buildings presents one of the more unique challenges for mechanical designers. Unlike other mechanical equipment required for these environmental systems, the air distribution equipment selection must combine a proper choice of engineered products, efficiently providing conditioned air to the space while adding architectural features which complement the interior design. Air outlet selection and application is no less important than any other facet of the HVAC system. Much time and money can be spent on the design and purchase of mechanical equipment, controls, piping, and ductwork. But if the air outlets are improperly applied or selected, the entire system could be considered a failure. With today's emphasis on occupant comfort, air quality, and energy conservation, the proper selection of air outlets cannot be overlooked. It is the intent of this Price training module to provide a concise approach to the proper selection of overhead air distribution outlets. Selection fundamentals. Performance factors. Several factors influence the selection of an air outlet. These factors can be divided into two groups: performance factors and design factors. When making an air outlet selection, it's important to keep in mind the outlet's performance factors. These factors include throw, drop, spread, sound, and pressure drop. Throw. Throw is by definition the distance the air is projected out from the outlet face. When discussing throw, we must reference it to a specific air velocity, which is called the terminal velocity. Most often, throw is referenced to terminal velocities of 150, 100, and 50 feet per minute. These velocities are indicated as T150, T100, T50 respectively. Throw is primarily a function of the mass of the air being discharged by the air outlet and the induction rate of the air outlet. The throw can therefore be reduced by decreasing the airflow from the outlet or selecting an air outlet with a high induction rate. Drop. Whenever cool supply air is introduced into a warmer space, its natural tendency will be downward movement. The vertical distance which the air jet extends below the ceiling is called the drop. Similar to the throw, we discuss the drop reference to a specific terminal velocity. For simplicity, we use the same three terminal velocities as for throw, 150, 100, and 50 feet per minute. If the supply air projects into the occupied space, uncomfortable drafts will occur. Drop can be minimized by utilizing the surface effect of the ceilings. Outlets located in or near the ceiling will exhibit less drop than outlets located on exposed ductwork. Reducing the supply air volume and increasing the supply air temperature will also reduce the drop. Spread. Spread is the horizontal width of the air jet being discharged by the air outlet. Delivering the air in a spread pattern tends to reduce both the throw and the drop of the air outlet. As with throw and drop, we discuss spread reference to a specific terminal velocity. Again, the same three terminal velocities are used to discuss spread, 150, 100, and 50 feet per minute. Dissipating the airstream over a wider area increases entrainment and reduces the mass flow per unit surface area. Sound and pressure drop. Sound and pressure drop are important considerations when selecting an air outlet. Pressure drop is important because this will affect the size of the fan required to push the air through the ductwork. If the air outlet pressure drop is too high, an oversized fan may be required. Air outlets are often selected to have a static pressure drop of 0.25-inch water gauge or less. The sound level of the air outlet at the prescribed airflow is also important. ASHRAE has published a design guideline for HVAC system noise levels for a variety of room types in the application's handbook. This information has been reproduced in the Price all-in-one catalog. Air outlets should be selected so the sound level at the specified airflow falls within the recommended sound level range for the specific room type. If the sound level is too high, it can be distracting and unpleasant for occupants in the room. If the sound level is too low, that can also be unpleasant for occupants. Some sound from the air outlet is necessary to serve as white noise and mask the other noises in the space. Without this white noise, phone conversations from adjacent desks will be more clearly heard. Virtually any noise in the space can become a distraction, as it is no longer masked. To summarize, throw is the horizontal distance from the outlet face to a point where the velocity of the airstream is reduced to a specific velocity. Drop is the vertical distance the airstream projects downward after leaving the diffuser face. Spread is the horizontal coverage of the airstream being projected outwards from the outlet. In selecting the size and the type of diffuser to be used, we want to choose a diffuser that provides an adequate air pattern and suitable sound levels for our environment while minimizing pressure drop for energy savings. In the following interactive section, we'll see how these factors work together to affect the throw and the drop in a room. You will have the ability to adjust the grill position, supply air temperature, and supply air volume to try to achieve the maximum occupant comfort level.
There's our employee of the month. That Bob's so productive.
I can't believe how much work I'm getting done.
What a hard worker.
I love my new office. 3 reports down, 1 to go. What the? What the? Brr. Thank goodness it's Friday.
There's our employee of the month.
Selection fundamentals. Design factors. Now that we have a better understanding of the performance factors, let's examine the design factors that you should consider when selecting your air outlets. These factors include function, location, air volume, and natural convection. Function. The most obvious question is that of primary function. Will the air outlet be used to supply air to the room or return air from the room back to the air handling system? Supply air outlets come in a variety of styles: ceiling mount, sidewall mount, floor mount, adjustable pattern controllers, fixed pattern controllers. There are a variety of discharge patterns available, some with long throws, some with short throws. Similarly, there are several different styles of return outlets. Typically, these all have fixed blades. However, blade styles and spacing can vary. Return outlets can be ceiling mounted, sidewall mounted, or floor mounted. All these points, as well as the aesthetics of the space, must be considered when selecting the supply and return outlets. Location. Location of the air outlet refers to whether it's installed in the ceiling, in the floor, or in the sidewall. 2 factors can influence outlet location. These are the desired performance and architectural or physical constraints. The path the air takes from the supply outlet to the return outlet has a major effect on the comfort level in the space. If the return is located in an area where supply air flows directly into the return without transferring its energy to the space may be uncomfortable. So, proper outlet location will have a major effect on the performance of the HVAC system in the space. In some cases, the type of outlets which can be used are limited by architectural or physical constraints in the space. Supply and return outlets must be selected to provide the optimum performance in the space while satisfying the architectural constraints of the space. Air volume. The actual air volume required to handle the heating and cooling load will also have an effect on the model of outlet used. Generally, the larger the volume per outlet, the more difficult it is to handle comfortably. The distance the air is projected from the supply air outlet is a function of the mass of the air. If we supply all the air through a single inlet, This may result in uncomfortable drafts in the occupied zone. If too many outlets are used and the supply air volume per outlet is too low, the system will not properly mix the air in the room, and the air may become stagnant or stratification will form. Either way, the occupied zone will be uncomfortable. Some air outlets, due to design considerations and basic concepts, are more effective at handling large air volumes. Examples of these are the RCDA, SMD, and SCD. These air outlets have high induction rates, which means that they will mix quickly with the room air, conditioning the entire space and giving relatively short throws, thus reducing the chance of drafts in the occupied zone. Natural convection. Natural convection air currents created by cold walls, windows, or localized heat sources should also be considered when planning room air motions. For example, convection air velocities of over 50 feet per minute can be expected on some cold window applications and will, if unchecked, dominate the room air motion. The cold air falling down an exterior wall will actually pull the supply air jet discharged from the diffuser along with it, giving longer than expected throws and possibly uncomfortable drafts in the occupied zone. The air outlet may be required to blow warm air down the window or wall from the ceiling or up from the floor. Each situation would require different treatment and totally different outlet performance. The buoyancy effect of warm air makes it more difficult to blow down the cold window, while it would assist the throw of a floor outlet discharging upwards. During the warmer months, hot convection currents will flow upwards along the wall. In this case, the rising warm air can cause the supply air jet from the air outlet to trip off the ceiling prematurely, which may cause the supply air jet to enter the occupied zone sooner than expected, producing uncomfortable drafts. It's important to consider these air currents and allow for them during the outlet layout. Typically, exterior walls are washed with conditioned supply air to keep them at or near room temperature and greatly reduce the chance of convection currents forming. In the following interactive section, we'll explore how these design factors work. You'll have the ability to select a diffuser type, adjust its position and quantity to see how throw and drop are affected in a room. Notice what happens to the air patterns when you place diffusers too close to one another.
Finally, some fresh air. I don't feel so well. My productivity just increased by 33%.
Air outlets. An important step to efficient space comfort conditioning is the proper selection of air outlets. This section presents generalized descriptions and characteristics of the types of grills, registers, and diffusers which are commonly used in commercial air distribution applications today. Grills and registers. The term grill is commonly applied to any air outlet or intake that consists of a square or rectangular face and neck and whose facial appearance is made up of fixed or adjustable louvers, which may be used to deflect the air. A register is simply a grill which incorporates an integral damper for air volume control. Supply grills and registers usually have adjustable louvers and are available in single or double deflection models. The single deflection type includes one set of blades in the horizontal or vertical orientation. Air pattern is adjustable in one plane only. The double deflection type includes two sets of blades in both the horizontal and vertical orientation. Air pattern is adjustable in both the horizontal and vertical planes. Adjustment of the vertical blades provides spread control of the air pattern, reducing both throw and drop. Adjustment of the horizontal blades provides control over the deflection of the air pattern. Air can be directed up or down to suit the application. Supply grills or registers are most commonly mounted in the side wall within 2 feet of the ceiling. Vertical face bars allow for the widest range of control of the horizontal spread. Return grills or registers usually have fixed blades or core and can be located in the sidewall or ceiling. Linear bar grill. The linear bar grill is normally used where an architectural blend of the grill to its surroundings is required. These grills may be mounted in the side wall, sill, or floor, and may be used for supply or return. Louvers are fixed with 0.25 inches or 0.5 inches bar spacing and 0, 15, or 30 degree deflection. The linear bar grill can also be built with pattern deflectors and be used as returns. Linear slot diffuser. Linear slot diffusers incorporate adjustable pattern controllers in a multi-slot configuration. Slot sizes are available in 0.5 inches, 0.75 inches, or 1 inch widths, and a choice of 1 to 10 slots. Adjustable pattern controllers allow horizontal left, right, or vertical discharge for maximum flexibility. Typically used in ceiling installations, the linear slot diffuser is architecturally appealing, particularly when supplied in continuous lengths. Larger slot sizes are available in 1.5 inches, 2 inches, 2.5 inches, or 3 inches for higher capacity applications. Round ceiling diffuser. Round ceiling diffusers consist of several concentric cones or a plaque suspended below the ceiling line by an outer cone. Neck sizes are available from 6 inches to 36 inches, allowing a wide range of air volume selections. Adjustable models are available to provide either horizontal or vertical air patterns. The round diffuser's excellent horizontal pattern makes it ideal for variable air volume applications or for exposed duct applications. Due to the availability of large neck sizes, the round ceiling diffuser is often used where high flow capabilities are required. Examples of such places are supermarkets, gymnasiums, halls, and industrial applications. Square ceiling diffuser. Square ceiling diffusers consist of several concentric square cones or a plaque and a round neck. The air pattern is a uniform 360-degree horizontal pattern. This horizontal air pattern is maintained at extremely low flows, making it ideal for variable air volume applications. Sizes are available to suit standard ceiling modules 12 by 12 inches, 20 by 20 inches, 24 by 24 inches. Adjustable pattern models are available for horizontal or vertical air pattern setting. Louver face diffuser. Louver face diffusers are available with a square or rectangular face composed of a fixed modular core. This modular design allows the selection of 1, 2, 3, or 4-way air patterns. Available neck sizes are square or rectangular. In addition to the design flexibility, the louver face diffuser is popular with architects because the louvers do not protrude below the ceiling line. Louver face diffusers have the capacity to control and direct air in unconventional rooms such as long hallways. Perforated ceiling diffuser. Perforated ceiling diffusers are available with a square or rectangular face supplied through a round or square neck. Horizontal air pattern is achieved with deflection vanes located at the diffuser face or in the neck. The vanes can be configured to achieve 1, 2, 3, or 4-way air pattern. The perforated face blends in very well with the acoustical tiles of typical suspended ceiling systems and is therefore preferred by architects. Perforated return units, both ducted and non-ducted, are also available to match the supply units. Light troffer diffuser. Light troffer diffusers are designed to integrate with commercially available light fixtures in suspended ceiling systems. The troffer consists of a plenum section, air slot, and pattern controller. Troffers are available as single-sided or double-sided saddle units. Light troffer diffusers produce an excellent horizontal air pattern, ideal for variable air volume applications. This is also the most efficient diffuser in terms of producing optimum comfort conditions. Since the air slot is very narrow and integrated with the light fixture, it's also appealing from an architectural standpoint. Plenum slot diffuser. These diffusers consist of a factory-fabricated plenum with integral pattern controllers for vertical or horizontal air pattern adjustment. Plenum slot diffusers are easy to install as they are designed to lay in on suspended ceiling grids. This feature also provides flexibility for future tenant revisions. Diffusers are available in lengths ranging from 2 feet to 5 feet. They offer a choice of multiple slot widths ranging from 0.5 inches to 1.5 inches. Selection procedures. Outlet selection. The outlet type and size must be very carefully selected so as to provide uniform air temperatures and comfortable air velocities within the occupied zone. In addition, noise levels must be acceptable. If these criteria are met, then a high level of comfort will be achieved for the occupants of the conditioned space. In order to properly select and size an outlet, a number of performance factors must be taken into account. Throw. Achieving the proper throw for a specific application is critical to proper outlet selection. Throw data is usually presented at terminal velocities of 150 feet per minute, 100 feet per minute, and 50 feet per minute. Generally, outlets should be selected so that the throw at 50 feet per minute terminal velocity equals the distance from the outlet to the boundary of the conditioned space. In most cases, this criteria will produce acceptable results. When an air stream strikes a surface, it tends to spread and follow the surface until the velocity dissipates. The total horizontal and vertical distance traveled by the airstream is equal to the tabulated throw of the outlets. For high ceiling applications, it may be desirable for throw to exceed the space boundary and travel down the wall toward the occupied zone. However, penetration of the occupied zone should usually be avoided. In addition to physical boundaries created by walls or partitions, boundaries can be created by the collision of two air patterns. Where two patterns will meet, the outlets should be selected so that the throw of a terminal velocity of 50 feet per minute is equal to 1/2 the distance between the outlets. For high ceiling applications, it may again be desirable for the throw to travel downward toward the occupied zone. Throw is again equal to the horizontal and vertical distance traveled by the air stream. It should be noted that most catalog throw data is presented for isothermal conditions. In other words, the supply air temperature equals the room temperature. During cooling, the denser supply air will shorten the horizontal throw. When selecting outlets for VAV application, both minimum and maximum air quantities must be considered for throw. Although many models of outlets provide excellent horizontal air pattern at extremely low flows, throws may be reduced below acceptable limits. Slot diffusers and light troffer diffusers tend to maintain reasonable throws at low air volume and are therefore a good choice for this application. In many applications, it is desirable to limit the throw due to ceiling layout, walls, partitions, or other boundaries which may obstruct the air pattern and cause unacceptable velocities in the occupied zone. There are several methods which may be used to minimize throw from outlets. Spread. Spreading the air pattern dissipates the airstream over a wider area and increases entrainment. This reduces the mass flow per unit surface area, which in turn reduces throw. Some outlets, such as the SDA and the TBD8, are designed to produce a spread pattern due to their geometry. Others, such as the double deflection and single deflection series grills, have adjustable vanes. Air volume. Throw is directly related to mass flow. Therefore, a reduction in air volume per outlet will reduce the throw. This can be achieved by utilizing more outlets with less air volume per outlet. For linear diffusers or grills, the same thing can be achieved by dividing the outlet into active and inactive sections. Each active section handles a smaller quantity of air thereby reducing the throw. In order to effectively separate the air pattern, the outlet should be divided by minimum inactive length. Surface effect. When the primary air is discharged from the air outlet at high velocities, it creates a negative or low pressure zone to form between the air jet and the ceiling. This low pressure area causes the moving air mass to cling to and flow close to the ceiling surface and is called the Coanda effect or surface effect. This effect has a strong influence on the throw and drop distances of the diffuser. Good air distribution design makes use of room surfaces to help keep the supply air outside the occupied zone. Price diffusers are designed to take advantage of the Coanda effect by producing it within the diffuser, helping discharge the air in the proper direction. Drop. Since a velocity of 50 feet per minute or less is desirable in the occupied zone, drop should be limited to a terminal velocity of 50 feet per minute, 6 feet from the floor. Following are several methods of reducing drop for sidewall grills. 1. Mounting the grill close to the ceiling creates a surface effect and reduces drop. 2. Deflecting the air pattern upward reduces the drop. 3. Spreading the air pattern reduces the drop. 4. Reducing the air volume reduces drop. 5. Reducing the throw reduces drop. Drop for ceiling diffusers is rarely cataloged as it's normally of no concern. In standard cooling conditions, the air jet does not reach into the occupied zone and therefore is not cataloged. However, for applications with low ceiling heights or when large volumes per outlet are required, the drop should be considered. The following table is a guideline for maximum air quantity allowable for given ceiling heights to satisfy 80% or higher occupant criteria. Return grills. Return grills are typically selected for core velocities of 500 to 600 feet per minute. This will result in sound levels of NC 35 or less. The volume of air passing through the return grill is going to depend on the type of room the grill is to be installed in. In a standard office or similar application, the return air volume will match the supply air volume. In more critical applications, it's not uncommon for the room to be at either a positive pressure or a negative pressure in relation to the surrounding areas. This is achieved by returning less air than is supplied for positive pressurization requirements, or returning more air than is supplied for negative pressurization requirements. Typically, a difference of approximately 15% between the supply and return airflows is sufficient for pressurization requirements, though this may vary based upon owner practices and room use. Noise criteria. Most air outlets are cataloged with a single noise criteria sound pressure rating based on a 10 decibel room absorption. This NC value assumes an average room and an approximate distance of 5 feet from a single sound source. These assumptions are reliable for many applications and have been proven effective over many years. This table illustrates the ASHRAE recommended space NC values for many commercial air conditioning applications. Outlets should be selected so that the tabulated NC levels are within these design goals. All outlet sound data is for a single source. Allowances must be made for multiple outlets when this occurs in a space, since the overall noise level may be the resultant of more than one outlet. This table illustrates the additive effect of multiple outlets of equal sound. For a large area with a large number of outlets, consider an area of 400 to 600 square feet as the maximum area where more than one outlet will contribute to the overall noise level. Take the area to be square or of an aspect ratio of 1 to 2. By using an overlay on the diffuser layout, the maximum concentration of diffusers can be determined, and thus the overall noise level can be calculated. The above procedure is a simple and fast method of adding multiple air outlets which will provide reasonable accuracy. For a more detailed sound analysis procedure, which takes into account room size, distance from the source, and unequal sound sources, refer to the Terminal Unit Engineering Guide of the Price All-in-One catalog. Here's a case study. A 25 by 40 foot conference room is supplied with 8 LTF 24 LP 6-inch oval inlet troffer diffusers. Each diffuser handles 120 CFM, and all 8 are evenly distributed within the room. Let's determine if this selection meets the recommended noise criteria. The total area of the 25 by 40 foot room is 1,000 square feet. Due to the dissipation of sound, a 500 square foot area will be representative of the overall noise level, so we can consider an area of 500 square feet containing 4 of the 8 troffer diffusers. From the performance table provided, the noise level of an LTF 24 LP 6-inch oval at 120 CFM is 23 NC. From this table, the additive effect of 4 outlets is 6 decibels. Therefore, overall NC is 23 plus 6, equaling 29. This selection maintains a noise level between 25 and 30 within the recommended range. Conclusion. We hope that you've enjoyed this look at air outlet selection. We've explored many aspects of air outlet selection criteria, from design factors to performance factors to selection procedures. We've also seen that the Price air outlet product selection consists of a full range of components including grills and registers, linear bar grills, linear slot diffusers, round ceiling diffusers, square ceiling diffusers, louver face diffusers, perforated ceiling diffusers, light troffer diffusers, and plenum slot diffusers, which may be combined to suit a variety of applications. For more in-depth information on this topic, you can always refer to the Price catalog. Be sure to explore the rest of the units in this Price training module to learn more about air distribution as well as the extensive line of Price products available. You can contact your local Price representative or visit our website at www.price-hvac.com for more information.